Okay, now if you have a polar curve and you want to find its length rather than the area that it encloses, you need to remember a couple of things. The first thing that you need to remember is that you always have the chance to convert from polar coordinates to Cartesian coordinates. That's incorrect. There's an r in there. I'll fix that. That's r sine theta. And so x is always r cosine theta, and y is always r sine theta. So that's always an option that you have. And secondly, once you have made that conversion, you can use what you already know about finding lengths of parametric curves in Cartesian coordinates. So by doing that, you get this formula. I'll do that with you right now so you can figure out how that's supposed to be done. Here, x prime and y prime are derivatives of x with respect to the parameter, right? Usually the parameter is t, but right now, because I'm in polar coordinates, I'm assuming the parameter is theta, and I'm also assuming that r equals some f of theta, so that when I do r prime, that's dr d theta, okay? So whenever I do r prime, that's dr d theta. When I do x prime, that's dx d theta, and when I calculate y prime, that's dy d theta. So let me tuck this in a little bit. Oh, not what I wanted to do. So I'll go ahead and rewrite this y prime and go straight to the calculations with you to find out what the formula has to be. Okay. We're going to use x is r cosine theta, and then my x prime I'm deriving with respect to theta, so I'm going to use product rule, r prime cosine theta plus r cosine theta prime. So this is r prime cosine theta minus r sine theta. This is my x prime. And then my y prime will be, because y is r sine theta, y prime will be r prime sine theta plus r cosine theta using the product rule again. So now I gotta go back into this formula and calculate x prime squared plus y prime squared. I'm gonna do this on the right side here. So x prime squared plus y prime squared. I'm not sure if this is all gonna fit in here, but I'll try. There's not a lot of space here. Let me actually, now that I know I'm gonna need space, since I already know I'm gonna need space, let me squeeze this a little bit more and see how that goes. So x prime squared plus y prime squared will then be r prime cosine theta minus r sine theta squared plus r prime sine theta plus r cosine theta squared. It's going to be a bit of a longer calculation. We're going to be squaring a bunch of those terms, foiling it all. At the end, we need to get r squared plus r prime squared. You can follow along. I think it's a good idea. It's always good to know what to do when you're stuck, and I like knowing where formulas come from because sometimes I'm stuck and I don't know what to do. And if I know how to get to the formula, I can try, even if that takes me longer on a test or something. I can try and at least get some of the points, even if I'm not able to solve everything, right? If I lose the time to get to what I need to get to. Right, so let me go ahead and square this first term here. And I'm going to, with that, be getting r prime squared cosine squared theta plus r squared, if I square the second here, sine squared theta, and then minus 2r prime r cosine theta sine theta. Okay, this is the square of the first term right here. All of this is this. All right. Now let me go ahead and square this guy. So I will get, now I'm adding all on the same line. Note that I haven't written a second equal sign. I'm still on this same equal sign after the same equal sign. So if I had enough space, I'd be writing all of those side by side on the same line. Now I'm squaring r prime squared sine squared. Square the first, square the second, r squared cosine squared theta, and then plus the first times the second times 2, so 2r prime r sine theta cosine theta. And then if you pause for a second, you can see, now I'm going to write my next equal sign, you can see that this and this cancel. They are the same term with opposite signs. And also you can see that if you factor out r prime, you see r prime squared. I should say factor out r prime squared. You get that times sine squared plus cosine squared, which will be 1. So you only get r prime squared. And then on these other two terms right here, you can see them right there. If you factor out r squared, you'll also get sine squared plus cosine squared. Maybe I can write that down to make it very, very clear. Since I've taken the time to go through all this trouble, I might as well just show the entire thing. This is what I mean, which then turns into r prime squared plus r squared. And that is x prime squared plus y prime squared, which is just the same as this. And that is what I replace into my formula. I replace this into this formula inside of the square roots to get this one. Okay? So that's how you obtain this formula. If you're in a pickle, if you don't know what to do, but you do remember these two things, even though you've forgotten this one, you can always just do this. It does not take forever. It does not take very, very long, but it is ideal, it is better that you just remember this formula. It saves you a lot of time. Okay, so let's go ahead and solve an example. I have an example prepared here. Let me go up and up and up and up. Put it right here. Go ahead and solve this example with you. So we want to find the length of this cardioid. And the cardioid is given by this equation. R equals 1 plus sine theta. So if you remember, we plotted this cardioid before in a separate video. It was something, you can go back and watch it if you need to. It was something like this, like an upside down heart. And one thing that you can note about this cardioid is that the area here on the right side equals the area on the left. So I might as well, if I want to find, excuse me, not the area, I'm looking for length, right? So let me actually highlight this. The length on the right side equals the length on the left side. This is a symmetrical curve, and that is because the sine function on this interval of theta, if you look at it, this interval of theta here on the polar grid corresponds to theta between negative pi over 2 to pi over 2, negative 90 degrees to positive 90 degrees. This side equals that side because the sine values for these go between negative 1 to 1 at the exact same rates that these go on this side go between negative 1 and 1. And so the signs will be the same, which means the r's will be the same, even though it will be going downward. So if you integrate this, here's a problem that you're going to get. If you integrate all this from 0 to 2 pi, if you just do this directly, you will end up with a 0. Because right here you'll get signs that are increasing, so these are going to go up, and you're going to get signs after that that are decreasing, so r prime is going to be negative. So this is not going to be good. I think you'll end up with a 0. Maybe I'm wrong. You can always double check, but my choice will not be to double check this. My choice will be that to find the area, I'm going to integrate this between negative pi over 2 to pi over 2, but then that will only be half of the area that I want. So to remediate that, I'm going to double it with a 2 out there. So this 2 outside is my choice. Okay. See if you understand what I'm talking about. this is giving me, the integral is giving me only this length right here, and I'm doubling it to get the entire length, okay? I think trying to integrate directly from 0 to 2 pi is going to cause trouble. If you don't think so, you can always try it out. I haven't checked, but I've made that choice. Whenever I plot a polar curve and I see some nice symmetry or something, I see that I can use the symmetry to simplify my calculations. So I'm going to go ahead and solve this integral here. Okay, so I know r is 1 plus sine theta. R prime is going to be the cosine of theta because the derivative is taken with respect to theta. Theta is my parameter now, which is why I have d theta here. So I'm going to go ahead and write here and say that a equals to integral negative pi over 2 to pi over 2 square root of cosine squared, because that's my r prime, plus 1 plus sine theta squared d theta. Let me box this so nobody thinks that this equals my integral somehow. And so this is going to be, don't forget the 2. Very easy to make mistakes when you have this number outside that you're not supposed to do anything with it. Just gotta keep track of it forever. This is a 1, 2 sine theta plus sine squared theta. All that inside of the square root. These two I get to combine and make a 1 together. Together with this one, that gives me a 2. Two plus 2 sine theta, and that's what you have to integrate. See, this is I think this is a hard integral. If you look at it, there isn't a very obvious u sub that you can make with this in the way that it is. And I had to stare at it for a little longer than normal to decide what to do. My thought process was this: whenever I see an integral that has sines or cosines, I'm always looking for clever u subs that I can make. And a u sub that I generally make whenever I have sines is to have u equals sine, like this. But maybe I wouldn't even do that, right? Because this is inside of the square root. If I make u equals sine, I still have the square root of 2 plus 2u. That's still difficult to handle. So I'd ideally make this entire u sub for the interior of the radical, 2 plus 2 sine. This is the u sub that I'd like to make. Okay. I'd like to make a u sub such as this. But the problem is that if I do that, du will be, this is my thought process, du will be 2 cosine. And there's no cosines in sight. So my task then to be able to make the u sub that I want is to make a cosine show up somehow. So I need this sine to somehow be squared so that I can use that sine squared plus cosine squared is 1. And maybe, you know, if I can have a cosine squared as 1 minus sine squared, then a cosine shows up. So I'm trying to make sure that this sine gets squared somehow. So what I'm going to do here isn't obvious. Like I said, I had to think a little bit to make this decision. So what I'm going to do is inside of the square roots, so big square roots, I have a 2 plus 2 sine theta. So I'm going to multiply this top and bottom by 2 minus 2 sine theta. The reason for that being that this makes that special product a plus b times a minus b appear here on the top. These two equal a squared minus b squared. That's the difference of two squares. My a being 2, my b being 2 sine theta. And when I make that change, I end up with 4 minus 4 sine squared theta, still over 2 minus 2 sine theta. d theta. And now this top here, is 4 times this. You see, this top is 4 times that is circled on the right there. So it's going to be 4 cosine squared. So it will be 2 integral 4 cosine squared theta, still inside the root, but I can put a root for each. And so it turns out that the whole top of this fraction becomes 2 cosine theta. Right. It'll be 2 cosine theta. And here's another advantage to just taking this piece of the unit circle, this piece of the polar grid. Cosine is positive all the way on this part. So cosine is positive, which means I can simplify it with the root and just get positive cosine. I don't have to worry about absolute value of cosine here at all. And then I get this, 2 minus 2 sine theta d theta. And now it turns out that the u sub that I wanted to make at the beginning does not work anymore because I don't have any 2 plus 2 sine anymore, but I have a 2 minus 2 sine. So this idea, the idea of making this u sub, only worked as inspiration. What I'll do, in fact, is a different u sub. I'll do 2 minus 2 sine theta equals u. Yes, so then du is negative 2 cosine theta d theta, which is just negative this, you can see. So it's very, very convenient. So I'm going to make that u sub there. Not going to bother with limits of integration for now. I'm just going to change everything into a negative right here from the u sub. And then du right here divided by square root of u. I think that's correct. Then we're almost done. We're starting to see the light here. This is some negative 2 u to the power integral still. Let's go. So let's do this carefully. Negative 1/2 du. Then I add 1 to the power. Divide by the power. 1/2 from alpha to beta. And then I got to divide by 1/2, right? Which would be the same as multiplying by 2. So when I derive 2u to the power 1/2, I will get that 1/2 comes down from the power rule, right? And then when it multiplies the 2, the 1/2 of the 2 will cancel, and then it becomes negative 1/2. I think everything here is fine. So this is a negative 4 times the square root of u from alpha to beta. And then instead of just putting the u's, the alphas and betas, I'm going to go back to u being this, 2 minus 2 sine theta, just to make my life a little easier. I think it's easier. Maybe I'm wrong. 2 minus 2 sine theta, but that's the choice I've made. Go back to thetas, and then that's negative pi over 2 to pi over 2. We're almost done. So nice. So when I plug in pi over 2, the sine of, forgot the root, right? Still all of this inside of the square root. So all of this is still inside of the square root. And so when I plug in pi over 2, the sine of pi over 2 is 1, which makes this whole thing a 0. So this will be square root of 0 minus, and when I plug in a negative pi over 2, the sine is negative, right? So I will end up with 2 plus 2 like this, square root still. So this is going to be nothing here. It's going to be positive 4 times the square root of 4, so 4 times 2 which is 8. Look at how weird this is. To me, this is very, very weird. We have this cardioid, which is a strange sort of curve. Double check my math here. If you see any mistakes, let me know. But go back. I think the answer is correct. But go back to the sketch. This is this weird shape. It is defined using polar coordinates of sines and cosines. And its length has no pi's, has no square roots, nothing. It's just 8. I think this is very surprising.